Today we're going to finish on IP, the Internet Protocol, and in particular some examples for IP addressing, how you calculate IP addresses, how do you use them in routing tables. First thing, let me collect your homeworks, please. Homeworks. Make sure your name's on the top. Anyone else? Thank you. Thank you. Homework? Finished? When did you do your homework? When did you do your homework? I know, you did it in the previous section. You were smart. Well done. Thank you. Thank you. Anyone else? Ah, good. Thank you. Let's take this one. Names, yes. Thank you. Thank you. Just name. Nickname's not good enough. Anyone else? We will, but I've got the answers on the screen. We'll go through some questions now. Let's have a look at some of the questions. More. So I know who's done them.
I can't do that.
Have you done it? Zero answers, not really useful. You need to know, and we're not going to go through it, you need to know how to convert the binary to dotted decimal notation, okay? That's the easiest step, and vice versa. You also need to know the concept and the role of the subnet mask. In binary form, the subnet mask tells us, for the IP address, the 32-bit IP address, it tells us where the split is between the bits that identify the network, what we call, or I call, the network portion of the address, and the remaining bits that identify the device, or I call the host portion. So in this example, this subnet mask tells us that the first, how many do we have? First 22 bits in the IP address identify the network portion of my address, and the last 10 are the host portion. So our computers, our laptop, our phone, in fact not just our host but also routers, so more generally our interfaces are normally assigned an IP address. And not just an IP address, also a subnet mask. So in fact we have two addresses. My laptop, when I connect to the wireless LAN, has two addresses, an IP address and a subnet mask, where the subnet mask tells my computer which bits identify the network. Let's go through an example from your homework where it gave you some information and you need to fill out the rest. So let's just summarise with that. Let's consider this one here. So there are different cases you consider, and let's consider the one where what's given is, let's say it's the IP address of my laptop, which is 140.16.32.21. 21. And my laptop also has a subnet mask. So if I look into the details, I'll see these two values. This subnet mask, which I'll write here, 255.248.0.0. First, convert them to binary. This one's easier. 255 in binary. 8 ones. 248. How many ones? 5. In 8-bit binary value is 5 ones, 3 zeros. So 248 in binary and then zeros. There's our binary form of the subnet mask. And we do the same for our IP address. And my brain's not working. I've calculated it before. You can calculate with a calculator. Somewhere I have an answer. I hope. Someone will calculate it for me before I find the answer. I don't have an answer. 140 16 32 and 21. So convert our dotted decimal notation to binary for both our IP address and our subnet mask. And we use the subnet mask to tell us that the first 8 plus 5, 13 bits here, the first 13 bits of our IP address represent the network that my computer is attached to. So my computer with this IP address and subnet mask is attached to some subnet in the internet. What subnet? Well, the subnet starts with these 13 bits. And we can give a special identifier for that subnet. It's called the network address. That's an identifier to refer to a whole subnet. And it's obtained by taking those first 13 bits and setting the last 19 bits to all zeros. So if you take these first 13 bits and set the last 19 to zeros and then convert back to dotted decimal, what do you get? Well, the first 8 bits will be the same, therefore we'll get 140. And then we have 5 bits, the same as before, and then last 3 bits are 0, so we'll get again 16. And then these 8 bits are all 0. So remember, in the network address, these 19 bits are all 0. 0, 0 in decimal. This is our network address. It's an address that we can use to refer to the entire subnet, the entire network. So I can say that my computer with IP address 140.16.32.21, subnet mask 255.248.0.0 is on the subnet with address 140.16.0.0 and subnet mask 255.248.0.0. And your computer, if it's on the same subnet, must have the same first 13 bits. So all computers on the same subnet, this subnet identified by 140.16.0.0, must all start with these same 13 bits, and they all must have different values of the last 19 bits. My computer has this value. Your computer, if it's on the same subnet, must have a different value than my computer. So we can have unique addresses. IP address in dotted decimal and binary form, subnet mask in dotted decimal and binary form. For simplicity or for brevity, we can have another notation for the subnet mask. Because the subnet mask is always a sequence of ones followed by zeros, how many ones? 13 in this case. So we have this third notation called the slash notation. The subnet mask of 255.248.0.0 is the same as this 32-bit binary value, which is the same as slash 13. It's just a shorthand way to write the mask. This is the shortest form. This is the computer form that's actually used. So you'll often see this slash notation, meaning 13 ones, 19 zeros. So we may say 140.16.0.0/13 is the network address, because we combine the IP address and the subnet mask. And the answer here would be slash 13. The network address is 140.16.0.0. There's another, so a network address is a special address. It's special in that your computer cannot have that address. When you set up your computer or someone sets up your computer and gives it an IP address, it cannot be given the network address. So it's not allowed to be used. And some software will detect that. Other cases, if you do try to use it, may cause errors. There's another special address, the broadcast or directed broadcast address. That's used if you want to send a datagram to everyone on that subnet. Okay? Broadcast to everyone on a particular subnet. And the way that we determine it is similar to the network address. We take the first 13 bits and then set the last 19 bits to all binary ones. And then convert back to dotted decimal, and we would get, what do we get? Calculate the directed broadcast address in dotted decimal notation. The first 8 bits will be this, therefore 140, easy. Remember, what we do is set these bits to all 1. So we take the first 8 bits, the next 5 bits, followed by 3 ones. 23. 8 ones, 255, 255. If I send a datagram to that address, so that's the destination, then all of the devices on this subnet should receive a copy. That's the idea. Again, I cannot assign this special address to my computer. So that's the answer here. Then the question is, okay, we have a subnet, 140.16.00/13. How many devices can we attach to that subnet and give them unique IP addresses? 13 devices. Wrong. So how many devices can we attach to that one subnet? Remember, the rule is that all devices attached to that same subnet must have the same first 13 bits. And the last 19 bits must be different. So if we have 19 bits that we can change, we have 2 to the power of 19 possible values. To the power of 19 possible values. Thank you. You're going to mark other people's, so take a copy, make sure you don't get your own. If you get your own, then swap it with someone else, so you can mark and you can see the questions. we have 19 bits to play with. That is, we can, for my device, I can choose from any of the 19 or different values for those 19 bits, and for your computer, a different value. So in total, we have 2 to the power of 19 possible values with 19 bits. Except 2 values we're not allowed to use. The value when all 19 bits are binary 0, because that's reserved for the network address, and the value when all of those 19 bits are binary 1. That's reserved for the directed broadcast. So the possible values we have is 2 to the power of 19, because we have 19 bits here, minus that one case for the network address, and minus that one case for the broadcast address. That is 2 to the power of 19 minus 2. And whatever that value is the answer here. So in theory, on this one subnet, I can attach 2 to the power of 19 minus 2 devices and give them unique IP addresses. And you can do that same approach for all those other questions. We're not going to go through any more examples. We're going to move on to the harder parts. This is something that once you practice 3 or 4 times, it should be easy. Any questions before we move on?
What if you have more than network and broadcast address?
What if we have more?
Can it be a case that we have to minus, not 2, but minus 3 or minus 2?
In why can it be different than minus 2? Only if. Why do we minus 2? Because there's always one reserved for network and one reserved for broadcast.
So it's fixed?
Always, yes. There are some other special addresses that we're not allowed to use. So in very special cases, or very rare cases, there may be some addresses that other addresses we're not allowed to use. But I don't think we'll see them in this course. So for us, it's the number of bits, 2 to the power of, and minus those 2 special cases. Yeah?
Where is 2 to the power 19 come from?
2 to the power of 19 is because the subnet mask is 13/13, meaning there are 19 bits in the host portion. 32-bit IP address, 13 in the network portion, 19 therefore in the host portion. 13 plus 19 is 32. So 19 bits on the right-hand side, which is the number of bits we have to allocate addresses to hosts, to devices. That is these 19 bits. They represent one computer. A different value would represent a different device. With 19 bits, how many possible values can you have? 2 to the power of 19. (13 bits for the network portion, 19 bits for the host portion, the portion that identifies the device on that network. How many possible values? 2 to the power of 19, minus the 2 special cases you're not allowed to use. Okay. Clear?
Why do you have to minus the network address and broadcast address?
Because, let's try a different case. Let's say the subnet mask was /29. We have 29 bits in the network portion and 3 in the host portion, if the subnet mask is /29. What are the possible values for the host portion? Well, for 3 bits, we can list them. with 3 bits, there are 8 possible values. That is 2 to the power of 3 possible values. But this one's reserved. It's reserved for the network address. This one's reserved for the directed broadcast address. So we have 2 to the power of 3 minus 2 values left. 6 in this case. The same here, 2 to the power of 19 minus 2 values left. Make sure you can do the other questions. This is a homework task. The file is from 2010. So if you go to the website for the course and you find the 2010 version, somewhere you'll find this file. It's not too hard to find. And you'll also find the answers. Okay? The answers are on the website. So you can check. But make sure you try them yourselves before you look at the answers. You can check if you get it right. And again, the best way is to practice these. We want to go through a more complex case which uses the IP addresses to create some routing tables. So at the end of today we want to come up with some routing tables. Here's an internet. There are 6 hosts labelled H1 through to H6, and there are routers A, B, C, D, E, F, and there are some subnets. How many subnets? Calculate the number of subnets. And when you've done the evaluation, you'll tell me how many subnets.
Now do you know that the medium size is this one?
How many subnets in this internet? 4 is wrong. 24 is wrong. I'll say when it's correct.
5, 1.
12, 16,
Let's look. Remember
6.
that, so these are routers, okay? A, C, B, D, E, F, they are routers. In an internet, a router connects subnets together. So in this example, here's one subnet. So router C is attached to using some technology. We don't care what technology, but there's a link to host H4. We call this one subnet. Okay. And router C is connected to router D. We'd consider this another subnet. And similar, router C is connected to router A and a third subnet. So router C is attached to 3 different subnets. So a router connects subnets together. In this case, if you, I think in the question up above, it explains the labeling and so on, that we'd have 3 subnets that router C is attached to, and similar for the other routers. And note this one. So host 2 and host 3 are attached to a switch. This is not a router. This is a layer 2 or a data link layer device, like an Ethernet switch or an access point. It may be an access point here, where this is a Wi-Fi link and this is a LAN cable. We'd consider this one subnet. From IP's perspective, it's one subnet. There are 2 hosts attached and 1 router. So if I was to draw this, I may draw a cloud here. We don't care what's inside. We just treat it in terms of the Internet Protocol, one subnet. Draw some clouds. How many clouds will you draw?
6.
Not 6. Count them in this here. Here's one subnet. Look at the routers. Router A is attached to 1, 2, 3, 4. Then there's 5, 6, 7, 8, 9, 10, 11 subnets in this case. There are 11 subnets in this internet. If I draw it quickly, running out of... Something like that, if you look at it from the routers and the subnets, they're these cloud-shaped objects. Router A is connected to 4 different subnets, B to 3 subnets, and so on. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 subnets in this example. In this case, I've given the routers names A, B, C, D, E, F, and same as the hosts. And also I've given the interfaces names or labels. So for example, router C is attached to 3 subnets. It has 3 interfaces. Imagine there's 3 cables plugged into that router. It's a device with a cable coming from router A, one going to D, and one to H4. They're on 3 different subnets and each would have an IP address. So let's call the interfaces for router C, C1, C2 and C3. Same as my laptop, I have a wireless LAN interface, I have a wired LAN or an Ethernet interface and a Bluetooth interface. Except in my laptop I only use one at a time. My router here has 3 interfaces and it may use all of them. Each of those interfaces must be assigned an IP address. We'll see what IP address shortly. So that's the task, or your task is to assign IP addresses to the hosts, each of the 6 hosts, H1 to H6, and for each interface for the 6 routers. So C1, C2, C3 need an IP address, as does A1 to A4. And I want you to assign IP addresses, and by filling in the tables here, the host IP addresses and then the router IP addresses. But I give you some information. That is, I give you some of the IP addresses, or at least a portion of the IP addresses. Find the IP address for host H1. Try that now. Find the IP address for H1. Consider what subnet H1 is on. Maybe draw that subnet. See who else is attached to that subnet. And see if you can work out what the IP address of H1 should be. That is, fill in this value here and the subnet mask. Use the network diagram, this, and use the provided information, either in this table or on the next page, the router IP addresses. Find the IP address for H1. I've given you a hint, it finishes with 2. What are the other parts? the hint? Draw the subnet for H1. Here's H1. Here's that subnet. Anyone else attached to that subnet? A router? Specifically A1, or the interface A1. All devices on the same subnet, their IP addresses must have some similarities. In particular, the IP address of A1 and the IP address of H1 must have the same network portion. The first X bits must be the same, and the last bits, the host portion, must be different. So we need to follow that rule, which applies to all subnets. So, do you know anything about the IP address of A1? It's given to you, 60, 45, 12.3 /28. So in fact, you know the IP address of A1. Since H1 is on the same subnet as A1, it must have the same network portion. What is the network portion? If we convert this to binary, it's the first 28 bits. That's what the subnet mask tells us. Convert it to binary. $60. 45, 12 and 3. That's the IP address of router interface A1. And we know that the first 28 bits must be the network portion. First 8, 16, 24, 28 bits. And by definition, or the rules are that any device on the same subnet must have the same network portion. So the IP address for H1 starts with the same sequence. Same first 28 bits, and the last 4 bits must be different. That's the host portion. So the router was 0011. For H1, what are the last 4 bits? Because the table gives you some value. Should be 2, shouldn't it? Because it's in the table in this case. I've given you some of the information, you need to fill out the rest. So there's the IP address for H1, because it's on the same subnet as A1, and therefore the same network portion, the same first 28 bits. And the last 4 bits are different. And convert that back to dotted decimal. So you have the answer for H1. So, and you can do that for, I think, all of the others, or most of the others. That is, because I've given some information, you look at who's on the same subnet as a particular device, find out the network portion, and then choose the host portion. And I think you can complete the IP addresses for all of them. In some cases, you can choose values. That is, there are multiple correct answers, so long as it follows the rules. The rules being that all devices on one subnet have the same network portion and a unique host portion. And the other rule is that all of the subnets have a different network portion. All of the subnets, the 11 subnets in this internet, must have a different network portion. And within each subnet, all of the devices must have the same network portion but different host portion. If you can follow that, then it's quite easy to do it for the rest. You'll do that when you study for the exam. Any questions about that approach? Try it briefly for which one? H. Try it for F2. What's the IP address for F2? F2, the interface of router F that is attached to this subnet with hosts 5 and 6 on it. F2. You're supposed to be marked. We were going to have you mark other people's, but I think we'll not have time to go through all the answers. So if you haven't got your original homework back, you can get it back. You don't have to mark the others. You can find the answers to all of these on the website. What is the IP address for F2? Note that F2 is attached to the subnet which has H5 and H6, so you use the information for H5 and H6. This is a switch. That is, in this case, it's a device inside the subnet. From the perspective of IP addressing and the internet protocol, we ignore its operation. We just say that inside this cloud there may be many devices, many cables. One of them in this case is a switch. But it's only the hosts and the routers that are involved in the internet protocol. That is, they get IP addresses, and when we forward via them. What do we get for F2? 200. Let's look at H5 and H6. H5 is 210.5.6/24, meaning the first 24 bits of this address are the network portion, and meaning therefore F2 must have the same first 24 bits. So convert this to binary, take the first 24 bits, give them to F2. The last 8 bits can be whatever you choose. But in fact, I think in the table, the last 8 bits must be decimal 1, because I give you the decimal value 1. So the first values here will correspond to the first 24 bits of H5. And here's a shortcut. The approach is you convert this to binary and then take the first 24 bits. Copy to F2 and then convert back to dotted decimal and you get the answer. But the shortcut is that recognizing we don't have to do the conversion to binary, because we can see with a subnet mask of /24, what that means is that the first 24 bits, in dotted decimal notation, it's the first 3 decimal numbers. Because this number is 8 bits, 16 bits, at the third dot it corresponds to the 24th bit. So with a subnet mask of 24, it tells us the first 3 dotted decimal numbers are the network portion and must be copied to F2, and the last decimal number is part of the host. So in fact, we can recognise only because of the subnet mask this special case of /24, we can just simply take 200.10.5 and copy to F2. Same with H6, 200.10.5. A subnet mask of /24 means the first 3 decimal numbers are the network portion. A subnet mask of /16 would mean the first 2 decimal numbers, and /8 is the first 1 decimal number. If the subnet mask is 8, 16 or 24, you can convert to binary, but you may take a shortcut and not convert to binary and just take the decimal notation. If you do not understand that, always convert to binary. Take this, convert to binary, take the first 24 bits, and then convert back to dotted decimal. But if you can work out the shortcut, it may save time in exams and in real life. So F2 becomes 200, 10, 5 dot, where that's the network portion. And the host portion, F2 is 1, /24. And then you can do that for all of the other addresses in that table. We'll not do that now. Any questions on how to do that? Yep. So for all of these other addresses, you'll be able to find, I think, unique values. With one case, H2, H3 and A4, H2, H3, A4, they're all on the same subnet. H2, H3, A4, therefore they all need the same network portion, but the information in the tables doesn't tell you which values to use. H2 is something something 13.1, H3 is something something 14.1, and A4 is something something 12.1, and they all have the subnet mask /22. What is the something something? In fact, you can choose any value. Any value, so long as it doesn't conflict with the existing values. So it's not the same as the existing values. So
not exactly the same.
not exactly the same.
Like it can be 130 and 130 and 4.
Yeah, possibly that's an answer. 134.12.1. And then H2 and H3 would be 130.4. Okay? So in this case, you get to choose any value, so long as it doesn't conflict with the existing values. So there are multiple correct answers there. What value did I choose? I chose 70.2 for no particular reason. For H2, H3 and A4. You can choose different values. I've removed our entire network, but here's one subnet. Let's give it a name. Let's call it net 1. Okay. So we can refer to that particular subnet, call it net 1. What's the real identifier we should use for that network? Try and calculate the identifier that we can use to refer to net 1. We have a special network address. Remember, a network address we use to refer to a particular network. What is the network address for net 1? Find the network address for net 1. That is the network with host 1 attached.
This means
Okay, so for a network address, the host portion must be all binary zeros. So on this network, let's call it net 1, we have H1 and A1. We know their IP addresses. Look at the binary form. This special network address, the network address for net 1 is that we take the network portion, the first 28 bits, and set the host portion to all zeros. So 0, 0, 0, 0 in binary. Convert to dotted decimal and we get 60, 45, 12, 0. That's the network address. So instead of me calling it net 1, I can call it 60.45.12.0/28. It's just a formal way to identify that network or that subnet in the internet. Instead of having a label like net 1, we have an IP address. And we can do that for the others as well. Let's say net 2 is this one. And then net 3 has host 4 and net 4 has host 5 and 6. Find the network address for net 4, which is this one. What's the network address for this subnet? And I'll give it to you for the others, at least the ones I've used. Find the network address for network 4, which is the subnet that contains H5 and H6. The values I've used for net 2 and net 3. Net 1 contains host H1, net 2 hosts H2 and H3, net 3 H4, and net 4 is the network that contains H5 and H6. What is its network address? .10.5.0/24. Because we know F2, we calculated before, F2 is on that subnet. F2 has the address 210.5.1/24. The /24 tells us the first 24 bits, or the first 3 decimal numbers, represent the network portion. The last is the host portion. Set this to all zeros in binary, and we simply get 0 in decimal. We get 200.5.0/24. And the other subnets can have addresses, network addresses as well, but we won't need them at this stage. We don't have time to calculate them. Any questions on how to find the network address? Take the network portion, set the host portion to all binary zeros. That's for the network address. It's used to refer to an entire network. This is the answers that I've calculated before. I've just listed those 4 networks, net 1, 2, 3 and 4, the network addresses. That's what's on the board. So you can find the IP addresses for the devices. The next part, which we will not go through, it's easy to do, I allocate costs to the links. Find the least cost paths. And it takes a bit of time, but you can find what is the least cost path from C to F, from C to B, C to A, C to D and C to E. Find the paths and find the costs. We will not go through that. I'm sure you can do it if you have to. It's just a matter of looking at each of the possible paths and choosing the least cost path. I've done it, and sorry, the answers I've calculated before. You don't need to record this. We'll come back to it when we need it. I've found that if we're at router C and we want to get to router B, the least cost path is C to A to B, and it has a cost of 5. That's from the network diagram in the question. And from router C to E, the least cost path is C, A, B, E, and the cost of 9. You could create, or you could fill in those values given the costs and the network diagram. We will use this to create our routing tables. So I'll come back to it in a moment. So assuming we've calculated that, we've given IP addresses to all of our devices, we've found the least cost paths between routers. Now what I'd like to do is give routing tables to each of the devices, create the routing tables. Let's try and do that. First, consider the hosts. Hosts have routing tables. Remember the basics of a routing table. To reach this destination, the next router in the path is this. I've given you the value for host 1, the routing table. What I've given you is saying, if we're at host 1, if we want to reach any destination in this internet, the star means any value, then we will send our IP datagram to the next router identified by 604512.3, which is our A1. If we're at H1 here and we want to reach anyone else on the internet, H2, H3, H4, H5, H6, then we'll always send to A1. And then it will be A1's job to send to the next router and so on. But from H1's perspective, the routing table is quite simple. For all destinations, send to A1. And this is just the IP address of A1. Then you do it for H2, H3, H5, and H6, and H4. I've basically given you the answers for those in the question because all you need to do is once you've found what the IP address is for A4, and that was in the previous question, just write it down here. In the routing table, we don't store the label A4, we store the IP address. The only reason in this question I've written A4 is just to help you so that we can identify which interface we're talking about. But in real life, in the routing table, the IP address is stored here. Let's go back to our network diagram to explain that. H1 wants to send to H6. Where does H1 send to? If we want to get to destination H6, where should it send to? A1. If we want to reach destination H5, where do we send to? From H1. If we want to reach any destination, where does H1 send to? A1. There's no option. Okay? There's no choice. That's why the routing tables are very simple. To reach any destination, send to A1. And it will be the same for the other hosts. H4 always sends to C3, H5 to F2. So the routing tables for the hosts are easy, in this example at least.
If there are choice to choose the subnet, which one do we choose?
So the question is, if there's a choice, which one do we choose? There's no choice in this example for hosts, but there is a choice for routers. H1 has a datagram to send to H5. It sends to A1. Now A1 has a datagram to send to H5. Where does it send? A1 has this datagram, destination H5. Where does A1 send to? It sends along the least cost path. The options are either B1, C1. Which one does it choose? We're going to skip the step, but we could calculate the least cost paths. If we know the costs of each link, which was given in this part of the question, you can find what is the least cost path from A to F. The answer I've calculated before. The least cost path from A to F is ABDF, and it has a cost of 8. Therefore, when router A has a datagram destined to someone that router F is attached to, it will send to B. When B receives it, it will send to D, and D will send to F. So you could calculate these. I've calculated them for you in this case. It just takes too much time. So if A wants to send to F, send to the next router B. If A wants to send to C, send to the next router C. And now the question was, who do we send to from router A? Well, that's our routing table for router A. To reach a host on network 1, where do we send to? For network 2, network 3 and network 4. Network 4, remember, is attached to F. It was the network with hosts 5 and 6 attached. So to reach a host on network 4, send to B, in particular B1. Let's try and draw that. I'll draw a portion of the network. Here was C, I think C3. Here's B1. And F was over here. And H5 and H6, this is network 4. F, the router F, attached H5 and H6, we call this network 4. From router A's perspective, if it has a datagram destined to network 4, it must get that datagram to router F. Which path to take to get to F? You find the least cost path and find the next node in that least cost path. And from the table that I've shown previously, the path should be via B. If A wants to reach F, send to B. In particular, send to B1. And that's what's captured in this routing table. If router A wants to reach someone on network 4, send to the next router B1. Instead of using network 4 and B1, we use the actual network address and the router IP address. If router A wants to send to someone with network address 200.10.5.0/24, then send that IP datagram to the router with IP address 130.10.0.2/16, which is in fact B1. It would send to B1. B1 would do the same. Look in its routing table to determine who to send it to. So we're trying to create this routing table. Can you do it for network 3?
Why network 4 goes to B1? Because this is network 4, right?
Yep. A question is, why do we go to B1? Let's go back to our network. If we're at router A, we want to reach this network. Okay, network 4. First note that the router attached is F. So in fact, if we're at A and we want to reach H5 or H6, we need to send to F. Which path to take? Well, we use our path cost information, which is in a question here. If we want to get from A to F, which path? Well, find the least cost path. It turns out if you check those paths, the least cost path is A, B, D, F, with a cost of 8. In this case. If you go A, C, D, F, it's 11. If you go by E, it's 9. The least cost path here is A, B, D, F, a cost of 8. Therefore, if A wants to reach F, send to B. And that's captured in the routing table. Here, if A wants to reach F, more precisely network 4, send to B, specifically interface B1. And this is the IP address for B1, this is the network address for network 4. Okay? Clear? You see some special cases in this routing table. If A wants to reach network 1, I say send direct. That means do not send to another router. If A wants to reach network 1, A is directly attached to network 1. We don't need to send to another router to get to network 1. We say send direct to that host or device on that network. If this is a Wi-Fi network, then we'd create a Wi-Fi frame and send it to the destination. So I've simplified by saying if the destination is network 1, there is no next router, simply send direct to the destination. The same applies for network 2, because A is also attached to network 2. That's the one with H2 and H3. If the destination is H2, A will send direct to H2. If the destination is H1, it will send direct to H1. If the destination is H5, it will send to B1. And if the destination was H4, I think it sends to C3. Or C1, sorry. And you can do that, you will do that in practice for your exam for the other routers. Router B, C, D, E and F. And as a result, you'll have the routing tables for every device, for all hosts and all routers in the network. Once you have the routing tables, it's easy. When you have a datagram, look at the destination, look up the routing table and see who you send it to until it reaches the destination. So, we've finished our evaluation, so we can go for another 10 or 20 minutes today. There's no problems if we're over time. Everyone's happy to go for another 20 minutes? No? Okay, let's finish up. Let's summarise on what we've done in these steps. Given a network, given an internet, we have multiple subnets. We assign IP addresses to the interfaces attached to each subnet. In particular, we assign IP addresses to hosts and interfaces of routers. And the rules are every subnet must have a unique network portion in the internet. This subnet has one network portion. This has a different one, okay, that identifies the subnet. Within one subnet, every device must have the same network portion but a different host portion. So C3 and H4, same network portion, different host portion. And that's the rule we follow to allocate IP addresses. Once we've allocated IP addresses, although we've skipped over it, we can calculate the least cost paths. If we know something about the costs, calculate the least cost path from source to destination. We can determine the network addresses. Remember, the network portion is the same. The host portion is all zeros, all binary zeros. That's the network address. And then we use that to fill in the routing tables, where the routing table says to reach some destination, what is the next router in the path? Normally for hosts it's very simple, because normally a host just has one next router. There's no choice to make. But for routers it's more complex because we have multiple possible paths to take. And in this example question, we consider just 4 possible destinations, net 1 through to 4. In a larger network, there may be many possible destinations. And of course, our routing table may expand. And in the routing table, we don't store things like net 1, direct, and C1. We store IP addresses, okay? Network addresses and IP addresses of interfaces. So here's a network address. Here's an IP address for B1. Out of time for today, and that finishes our topic on the internet. Tomorrow we will start the almost last topic on TCP. So we'll cover TCP tomorrow and next week. There's one other topic on HTTP, but you've done that in your exam, in your assignment, so we only need about 30 minutes on HTTP. So one more main topic which will start tomorrow. You have your assignment marks are online. Check them.